Hello everyone, and in this video we're going to discuss acceleration and force. I think in the last video we briefly mentioned that acceleration was a change of speed, and we talked about speed and motion in the last video, but when things change their speed, that means that they experience force, and that means they can move other things, and that's what we're going to look at here. So let's start with acceleration, and just to recap, things have to start moving and they have to stop moving, and so acceleration is the change in speed. If your speed goes from 3 meters per second to 6 meters per second, then you have accelerated. So like velocity, acceleration has a direction. If the object speeds up, then the acceleration is in the direction of movement. If an object slows down, then the acceleration is opposite to the direction of motion, the negative acceleration. Also, if an object changes direction, there is also an acceleration there. It is an acceleration across the direction of motion. That means that the object's speed changes differently in different dimensions. X, Y, and Z. So let's just get to the calculation, and keeping it simple, if an object is moving in a straight line, then its acceleration can be calculated by this equation. You take the final speed and then you subtract the initial speed of the object, and you divide that number by the time it took for the object to change speed. So using this equation, you can calculate the change from any initial speed over any time period. And you can see that a speed minus a speed gives us a change in speed, and that change is also measured in meters per second. And on the bottom of the equation, the time taken for the change is a time in seconds. So what we end up with is meters per second divided by seconds. Effectively, we're dividing by seconds twice. And so what we end up with as our units of acceleration is meters per second squared. So as we did with speed, let's look at the formal version of the equation. Here it is. We're using A for acceleration in meters per second squared. And then we have dv over dt. So dv is a way of writing the change in speed. It's actually related to when we saw the triangle delta in the last video, and it's over the change in time dt. So it's a way that you will see rates of change written in mathematical terms. And there we have the symbolized form of the last equation. We have vf, the final velocity, minus vi, the initial velocity, over t, the time in seconds. Another way you often hear acceleration being described is as the change in speed divided by the time taken for that change. So here's a couple of example questions on acceleration, which I'll leave you to think about for yourselves. Find the acceleration of a train whose speed increases from 7 meters per second to 17 meters per second in 120 seconds. The next one, a bicycle accelerates from rest to 6 meters per second in 2 seconds. What is the bicycle's acceleration? And we'll mention as we pass here that at rest is a way of expressing that something is not moving. In other words, that it has a speed of 0 meters per second. So if you accelerate from rest, that means you are not moving when you begin to accelerate. Another thing we can do with our speed data is have a speed time graph, and that means that we show the time on the x-axis again, but this time going up the y-axis we have speed in meters per second. And the speed time graph allows us to see the speed of an object at any time during its journey. And that can be quite useful. It also leads us to some very important pieces of information about the moving object. So what do you think the slope represents here? If you think back to the last video, we said that the slope of a distance time graph is the speed. Well, the speed is up the y-axis this time, so what does the slope represent? Remember that when something is plotted against time, the gradient represents a rate of change. So, have you thought about it? In fact, the gradient is the rate of change of speed. In other words, it's the acceleration. It's the rate at which the speed is changing value, and that is the value on the y-axis. We can further demonstrate that the area under the graph is the total distance traveled. And what do I mean by that? Well, if you imagine making a box 1 second along the time axis and up 1 meter per second on the speed axis, then you have a 1 by 1 box which represents 1 meter of traveled distance, and you can use that area to find the whole area under the graph in units. So it's a little bit more complicated than that, obviously, and the mathematics we use to prove this is called calculus, and this is something you'll come to in a later course. It's another invention of Newton's, but it's also an invention of Leibniz, and in fact calculus is the name given by Leibniz. The name that Newton gave it was fluxions, which is the mathematics of flux, of changes. In either case, it's a very, very useful form of mathematics, and you'll see exactly how useful in a further course, I'm sure. So we're going to jump now to force, and first of all, what is force? A force is a push or a pull, so it is any effect that will change the motion or the shape of an object. Now we're going to be dealing mostly with motion in this regard, but we will look briefly at things like elastic potential energy, which are due to the change in the shape of an object. So next we have to understand how force works, and for starters you might already understand that a force must have a direction. If you know what a force is, it seems like it must have a direction, which means that it's a vector quantity. And if it's a vector quantity, then multiple forces can act in many directions on one object, and that adds up to the overall force that is experienced by the object. Accurately putting together all these different component forces is one of the challenges of the mechanics of force. So how do we do that? Well, we add up all the forces acting on an object, and that gives us what is called the net force on the object. When more than one force is acting on an object, then the net force determines the overall motion of the object, remembering that force is what gives rise to motion. So we need a simple way to show systems of forces, and you might be seeing what's going on from the pictures on the last slide. We often use arrows to represent forces. So here we can see some examples of arrows representing forces just randomly in space, and the third example there on the right shows that two forces are acting on. So here we can see examples of forces acting on an object. There's no convention really on whether you have the arrow acting away from the object or into the object, as long as you keep it consistent. So here we can see an example of some forces acting in various ways, and the size of the arrow represents the size of the force. That is the magnitude of the vector. That's something important to remember, that although it isn't actually a physical distance, the size of the force can be treated in the same way as a physical length. And that means we can use Pythagoras and trigonometry to work out the components, which we will talk about briefly at the end of this unit. So here we're going to define balanced forces, and as you can probably imagine, the next thing we're going to define is unbalanced forces. You can probably see what's going on though. If we show all the forces acting on an object, and we are focusing on a single direction here, and we can put in the line of propagation of all of those forces, we can see that there are several forces, but overall they add up to 0 because there is 5 newtons acting to the left and 5 newtons acting to the right. So the net force on the object is 0. This is what we call balanced forces. So it's reasonable next to define unbalanced forces, and they are simply just forces that do not cancel each other out. And I'm sure some of you can imagine what's going on here. In this object's case, we have 10 newtons acting from the left, pointing right, and 20 newtons acting in the other direction. So assuming that the friction is 0, what is the net force on this object? It's very important that we exclude friction from this situation. So if the forces acting on an object are unbalanced, then the net force is not 0. What this means is that the object is going to change its motion, and if it changes its motion, that means that unbalanced forces give the object an acceleration. So let's just cover that example from the last slide. It's not particularly complicated. So we have, if you remember, 10 newtons acting to the right and 20 newtons acting to the left. So what we have to remember is these are vector quantities, so direction is important. The good news is that all of them are acting along a single axis of propagation, in other words, a single line for all the forces, which means we can just simply add and subtract the forces. And so the force on the object is equal to 5 plus 5, that's the forces from the left, plus minus 20, which is the big force from the right, and that gives us an overall force of minus 10 newtons, which means that the object experiences a force of 10 newtons to the left. So because the forces are unbalanced, the object experiences the acceleration, and that is in the negative direction because the forces from the negative direction outweigh the forces from the positive direction. So this is how force actually relates to motion in the real world. So it's time to move on. So far we have defined motion very clearly, and we've now talked about how motion changes and what causes it to change. Motion changes by acceleration, and it's force that creates that acceleration. So the amount of acceleration a force creates depends on how big the object is, and this is something we haven't talked about yet. We haven't talked about how the mass of the object comes into play. And so this is where we have to look at the work of one of the most famous scientists of history and his 3 laws. For now we'll leave off with the business of force and acceleration. I hope that's cleared up some of the issues for you and the confusing points. I'll see you next time.